Hey chemistry! In today's video, we're just going to talk about a couple more details about electron configuration. So in the last video, we talked about how to write electron configurations, but there's a couple special circumstances that we have that we want to address now. So we're going to talk through ions. Ions is going to lead us to something called isoelectric species, and then I want to walk you through something called the noble gas configuration that I swear you'll like. So let's get started. First of all, talking about ions. So we talked about what an ion is in the beginning of our class. And we talked about how an ion is something that either gains or loses electrons. And because electrons weigh so little, that doesn't change their mass at all. What that changes is their charge. So really, an ion is an atom that has a charge. Now, the charge is going to depend on whether the atom gains or loses electrons and how many electrons it gains or loses. So if in an ion that gains electrons, remember that an electron is a little particle that's negative. So if an atom gains electrons, it's going to have a negative charge. It's also going to have more electrons when you compare it to the element. If you compare the ion of something with its neutral element, the ion will have more electrons. And the number of electrons it has gained is going to be indicated in the top right of the symbol. So like F minus would be the fluorine atom that has gained 1 electron. So fluorines normally have 9 electrons. If it has gained 1 electron, now it has 10 electrons. You can also have something like O2 minus. That would be the oxygen atom that has gained 2 electrons. So oxygen normally has 8 electrons. It has now gained 2, which means it will also have 10 electrons. These two elements are called isoelectric elements. Iso, you may know from terms like isosceles or isosceles, an isosceles triangle, or isotonic. An isotonic solution has the same concentration as the thing it's being compared to. An isosceles triangle has sides that are all the same length. So iso means the same. And electronic is talking about the electronic structure of the atom, which is what we've been talking about, right? With all the N's and L's and M sub L's and all that good stuff. So an isoelectric species has the exact same electronic structure around it because they both have 10 electrons. They're both going to have those electrons structured into the same place. So I want you to look at the periodic table and find me a neutral element that would be isoelectric with these two ions. Pause the video here and go find that. And hopefully the one you found is neon. Neon has 10 electrons, normally has 10 protons, also has 10 electrons. And so neon would be isoelectric with the fluorine that has become an ion. We call it the fluoride ion. And oxygen's atom that has become an ion. We call that the oxide ion. One other fun fact, any electron that gains, or any atom that gains an electron or 2 or 3 and is therefore negative, we have a special term for that. They are called anions. Anions are negatively charged atoms because they have gained electrons. All right, let's do the opposite. If they have lost electrons, Okay, if something has lost an electron, remember, an electron is a negatively charged thing. So if you lose things that are negative, you're going to become more positive. So atoms that have lost electrons are going to have a positive charge. And if they have lost electron, the positively charged ion is going to have less electrons than the atom. I can put a little alligator in for our anion up there too. An example of this would be sodium. Let's just stay small. Sodium, for example, starts with 11 electrons. It now has a 1 positive charge. So that tells you that it has lost 1 electron to become positive. So lost 1 electron. It now has 10 electrons. And then let me give you an example that is not going to be isoelectric with neon. Notice that Na plus will also end up with 10 electrons and be isoelectric with neon. Let me give you calcium. So calcium forms a 2 plus ion. That means the normal calcium atom has lost 2 electrons. So take a look at your periodic table. See if you can figure out how many electrons the calcium ion ends up with. So the calcium atom starts with 20 electrons. We know from the 2 plus that it has lost 2 electrons. So now the calcium ion will have 18 electrons. Just like a negative ion is called an anion, a positive ion also has a name. We call them cations. So a cation has a positive charge, an anion has a negative charge. All right, so when we look at ions also can have we can also write electron configurations for ions. So the important thing here is to consider how many electrons the ion has, and then use that number of electrons to write out your electron configuration. Do not use the element or the neutral atom's amount of electrons, because if it's an ion, it now has a different number of electrons. So let's write electron configurations for a couple ions that we have up here. Let's do fluorine. So fluorine, I'm going to write an electron configuration that has 10 electrons. So I'm going to fill the 1s with 2, 2s with 2, and then 2p. So I have 4 already. I need 6 more. The 2p fills up with 6. Notice this is the exact same electron configuration as something else on the periodic table, and that something else is neon. So neon's electron configuration, 1s2, 2s2, 2p6. It's the same, thus the isoelectric nature of these two things. And notice fluorine's ion actually fills itself up with electrons until it forms a very, very stable configuration, as stable as a noble gas. Isn't that interesting? Let's look at calcium. We'll do the same thing for calcium. So calcium, the calcium ion, not the calcium atom. Let's draw the electron configuration for the calcium ion. We're going to use 18 electrons. Okay, so this would be a good place to pause the video and see what you come up with. Calcium 2 plus is going to have 18 electrons, so 1s2, 2s2, 2p6 gives us 10 electrons. 3s2, 3p6 gives us 18 electrons. Now notice normally if we compare calcium to the calcium ion to the calcium atom, we can see exactly where those 2 electrons are lost from. So notice the calcium atom ends in 4s2. If I remove those 2 electrons, then I get the calcium ion configuration. Same thing with fluorine. We can compare fluorine, the fluoride ion, to the fluorine configuration. 1s2, 2s2, 2p5. So in the case of fluorine, we're actually going to add 1 electron, and then that will get us to the ions configuration. So you will always be able to see from the atom to the ion where it has gained or lost electrons. And notice that both ions end with energy levels or valence shells that are completely filled. The 1s and the s and the p end up completely filled for ions, and that's always true. It's always true until you look at the metals. The transition metals get a little crazy in there, but we'll talk about the transition metals some other day. Okay, so that is your super brief intro to ions. We'll be talking about ions again in more depth. Ions tie very closely to the periodic table, so it's helpful if we talk about the periodic table a little bit and then get into ions. So we will recap ions again once we talk about the periodic table. But anytime you are given an ion with its charge, you can use that to figure out how many electrons it has and then to write out the electron configurations from there. Okay, last thing I want to talk about is a noble gas configuration. And I promise you're going to like these because they're a shortcut for you. They're going to make your life easier. So let me show you what a noble gas configuration is. You may have already noticed as you're writing out electron configurations for these atoms that are a little bit bigger, that they get a little bit repetitive and a little bit tedious. Like if we write out, let's say helium, fluorine, sodium. Well, actually, that's not sodium anyway, but let's do neon, sodium, argon, and let's just do calcium for fun. Okay, I'm going to write out the electron configurations for these atoms. See if you can beat me there. All right, so there's the electron configurations for all of these. If you didn't beat me there, pause the video now and catch up, and then we'll keep talking about noble gas configurations. So like I said, it gets a little repetitive, right? Notice they all have 1s's. If you go far enough, you're going to just start repeating the same things over and over. And as scientists, our time is valuable, and or we're lazy people, or efficient. I prefer the word efficient. We're efficient people, right? So we don't want to write the same thing over and over and over again. We want to find ways to make really good use of our time. And so what happens is you're going to take the noble gas and replace part of the configuration with the noble gas. So notice for helium, helium is a noble gas. Helium, neon, and argon are all in that 8th column. So they are in the noble gas family. And notice the noble gas family, like we talked about before, it's always has S and P shells completely filled. And that's true no matter where you go. Even if you go on the very bottom section, it's going to have every S and P shell, which are your valence shell, filled, and anything below that will be filled also. So noble gases are a really good stopping point for us. So anytime that your electron configuration contains a noble gas, you can actually write the noble gas instead of that part of the configuration. Let's look at helium and fluorine, for example. So fluorine's configuration is not quite neon's, right? Fluorine has one less electron than neon has. So you can't use neon to replace anything in fluorine's electron configuration. However, helium's 1s2 is contained inside fluorine's configuration. So fluorine's configuration can also be written with helium in brackets, and then you just write the rest of the electron configuration, 2s2, 2p5. So either one of these is okay for fluorine's electron configuration. The first one would be called fluorine's electron configuration. The second one would be called fluorine's noble gas electron configuration. Let's do the same thing for sodium. So notice sodium has neon on one side of it and argon on the other. So sodium does have the same configuration as neon right there, but it is missing part of argon. So we can't use argon. We can use neon. So let's write neon and then 3s1. And the noble gas configuration isn't super helpful for fluorine, but it's a really big shortcut for sodium, and sodium's only element 11. Imagine what this would do all the way down at the bottom of the table when you're dealing with like 150 electrons, right? You don't have to write every single one of those electrons into a configuration. You can just start with a noble gas amount of them and write what's left. Okay. Why don't you pause the video and try calcium? Try writing calcium's electron configuration as a noble gas configuration. Pause it here. And hopefully what you recognize is that argon's configuration is completely inside of calcium. So we can write calcium's configuration as argon in brackets. You have to put it in brackets. And then you can write everything that argon doesn't contain, which is the 4s2. Now, again, the periodic table is going to be really helpful in using this shortcut. So we're going to talk a little bit about the periodic table when we get back. And then you're going to see that this noble gas configuration thing is actually even more of a shortcut than you realize it is right now. Okay. Let me know if you have questions. I will see you in class.